Hi Year 11, this is your paper 2 for physics, so you can annotate your paper directly. That's probably the best thing for you to do. It would also be good for you to have a look at how much you've actually written on the page. So compare to me how much you've actually sketched out or kind of worked out on the page. If you try and do multiple choice in your head, you quite often make mistakes. Obviously not the case for all of them, some of them are straightforward, but just have a general look and see, does yours seem to have as much stuff on the page as mine? And if it doesn't, that's something for you to work on. So question 1, which two quantities must be known to determine the density of a material? This is just remembering the equation. So density is mass divided by volume. So I need to know both of those things to be able to work out density. Gives you B. That was easy if you knew the equation, but if you forgot it, you'd be wrong. In question 2, this is a little bit more difficult. Forces of 3 newtons and 4 newtons act at right angles as shown. What is the resultant force? There are a couple of ways that you could look at this. You could think about it just in real life. If an object is being pulled up and across to the right, it's not going to end up left or down, okay? So XZ doesn't make any sense. So that should hopefully help you. You don't close the triangle here because you've got tail to tail. And when we have tail to tail, we use the parallelogram method for finding resultant force. So remember, we draw a construction line that's parallel to each vector. And where those construction lines crosses, that's where the resultant ends up. But think logically, if I am an object and I'm pulled up first and then across to the right, I'm going to end up over here. So I should be looking for OY. Okay, that's the first thing. And then the second thing is to rearrange. So we've picked up this 3 Newton force and we've moved it so that it's on the other end, so that what we have is top to tail. Okay, and that means we can close the triangle, which gives us a right angle triangle where we've got 3 as the length here, 4 as the length here, and we're just using a squared plus b squared equals c squared from Pythagoras. So we've got 4 squared plus 3 squared is equal to r squared, gives us 25 equals r squared. So I then square root to find r, the resultant, and I get 5. It may just be worth also remembering that a right angle triangle that has 3 and 4 will always be closed with a 5, a 3, 4, 5 triangle. That's quite a common one. So that's it's quite a tricky one in terms of the diagram. There's a lot going on, but you really need to think about it. If you're an object at O and then you're pulled to the right and you're pulled up, your general direction is going to be upwards to the right. So that's OY. In question 3, a ball of mass 0.25 kilograms hits a wall at a speed of 16 meters per second. It then rebounds. This means it moves off in the opposite direction, back along its original path at a speed of 12 meters per second. I have to then remember that because it's in the opposite direction and velocity is a vector, the sign on it matters, and so velocity will be negative if it's going in the opposite direction. So although the magnitude is 12, it's actually a minus 12 for my calculations. What is the impulse experienced by the ball during its impact with the wall? Well, impulse is change in momentum, delta P. Change in momentum is the final momentum minus the initial momentum. But the mass of the object is constant, so I can factorize this and I can say, well, that's equal to mv take u. M is just 0.25. V is the final velocity is minus 12 minus the initial, which was 16, is equal to 0.25 times minus 28. So the change in momentum then is then 7 kilogram meters per second. And the direction of that is to the left, which is what the minus sign is for. But the actual value of it is 7. Okay, so that's what you needed to do there. In question 4, it is a Hooke's law question. A spring has an unstretched length of 3 centimeters. When a force of 60 newtons is applied, that's F, its length increases to 5. The limit of proportionality is not exceeded. So that tells us that it remains proportional, which means that the spring constant is a constant value. So first things first, we need to work out the extension of the spring. It started at 3, it went to 5. That's a gain of 2. Okay, so the extension x is 2 centimetres. We then need to remember Hooke's law equation, F equals kx, rearrange for k because the spring constant is what we're looking for, which is F divided by x. The force was 60 newtons, the extension was 2, gives me 30 newtons per centimetre there. Okay, in question 5, a cyclist is travelling in a straight line along a horizontal road at constant speed. I've highlighted the phrase constant speed because it's giving me some extra information, even if it's not explicitly writing it. Constant speed means no acceleration. Resultant force on an object is equal to the mass multiplied by its acceleration. Well, if acceleration is 0, resultant force must also be 0. So, if the cyclist is providing this driving force F to the left to make it move forward, there has to be an equal but opposite force from friction to balance that out so that the resultant is 0. So the magnitude has to be equal to F so that the overall force is 0. In question 6, excuse me, so the speed time graph shows the motion of an object. How far does the object travel at constant speed? So the first thing is to look at the graph and decide when the object was moving at a constant speed. Clearly that's when it's just a horizontal line so that my y-axis value of speed does not change. So I'm only interested in what's happening during this time. Speed is distance divided by time. I can rearrange that and say that distance is equal to speed multiplied by time, which you can hopefully see is the area under the graph. I'm doing a time value multiplied by a speed value, which gives me a distance. I only need the area in this section because that's how far it travelled while it was moving at 5 metres per second. It did that, so it did that speed of 5 metres per second for 10 seconds. So I've got 10 lots of 5 gives me 50 metres. Okay, so in question 7, a uniform beam. So the word uniform here tells us that the centre of the mass acts at the pivot point because the uniform beam is pivoted at the centre. The centre is where the centre of mass will be, so this means that the mass and the weight of the beam itself is going to direct through the pivot and there's no perpendicular distance. So the beam itself won't turn if it was just by itself. Excuse me. We add 2 identical masses, x and y. They're also placed so that the beam balances. So you can see that y would by itself make it turn clockwise, but x makes it turn anti-clockwise to balance this out. A smaller mass is then added to the position shown. Well, you can see that it's to the left of the pivot, so this small mass is going to contribute to this whole beam turning. So until we do something about it, by placing this small mass, this whole thing is going to tend to turn in an anti-clockwise, counterclockwise direction. Okay, so the small mass has contributed more anti-clockwise turning effects, so we need to reduce that. Okay, so we either need to reduce the anti-clockwise moment here, which we can't do because it says how can the masses be positioned, so we can't get rid of it, or we need to increase our clockwise moment to balance this anti-clockwise. So I know that by definition a moment is a force multiplied by the perpendicular distance. So what we know is that the force of this one's weight acting down multiplied by its perpendicular distance to the pivot has to be larger. Because we've now got it turning more anti-clockwise, we need it to turn more clockwise, so we need to increase the turning effect of this one. We cannot change its mass, so we can't change its weight, so we can't change the force. So what we have to do is change our perpendicular distance. So we know that if we wanted to increase the clockwise moment to account for this, we would need to increase y. So the distance from the pivot would need to increase. This isn't going to be one of the options. It says move y towards the pivot. If we were to move this inwards, it would actually reduce the turning effect, which would be a problem because it needs to balance this one. So what we need to do is we need to make this one's turning effect smaller by bringing it in so that these two can then add up to this one. Okay, so lots of you picked C, which doesn't make sense. Okay, so it's B. We need to move this inwards to reduce the turning effect of this so that it basically counters the extra turning effect that we got from this one. Okay, let's see if I can get all of this in. Ooh, almost. A little bit long, a little bit more. Sorry, right, there we go. Okay, in question 8, a trolley of mass 4 kilograms travelling with a velocity of 4 meters per second collides with a trolley of mass 2 kilograms travelling with a velocity of 2 meters per second in the same direction. Picture here. They then collide, and afterwards the 4 kilogram mass moves with 3 meters per second and the 2 kilogram mass moves with an unknown velocity that we're trying to work out. So this is a collisions question. We need to remember that total momentum of the system, so the two trolleys, is conserved. It is the same before and after the collision. Momentum is P, and it's calculated by the product of the mass of the object and its velocity. So before, we have the mass multiplied the velocity of this one, plus the mass multiplied by the velocity of this one. So we have 4 times 4, mass times velocity, plus 2 times 2. Okay, so that gets me 16 plus 4. So I've got 20 kilogram meters per second of momentum in total before the collision happens. Afterwards, we know we have momentum of this one, mass times velocity, 4 times 3, plus mass times velocity of this one, which we can write as 2 times v. So I've got 12 plus 2v. So I can say 20 is equal to 12 plus 2v. If I minus 12 from both sides, I get 20 minus 12 is 2v, is 8. To get v by itself, I have to divide both sides of the equation by 2, and therefore 8 over 2 is v, is 4 meters per second, gets me b. Okay. In number 9, this is one you either know or you don't. So the diagram shows an object moving at a constant speed in a circular path in the direction shown. A force acts to keep on the object, to keep it in the circular path. In which labelled direction does this force act when the object is in the position shown? Okay, an object tends to move in a straight line until a force acts on it. So if this object is spinning round clockwise, when it's at this point, its tangential velocity is upwards. So by itself, it would tend to go up. To keep it in the circle, we've got to push it in. You need to remember, and this is just a memory one, that the force to keep something in a circle always acts towards the centre of the circle. Always, always. Okay? So it's always directed towards that point, and D is the only option for that one. Please just remember that. In D, I've actually drawn a picture as well, so I'm going to zoom out. So the density of seawater is 1,030 kilograms per meter cubed. This is rho. Label this. The gravitational field strength on the Earth is 9.8. That's G. Atmospheric pressure, so the pressure because of the atmosphere, so the air, is 101,000 pascals. At which depth in seawater is the total pressure due to the atmosphere and the water equal to 513,000 pascals? Okay, so first things first is we need to work out the pressure that the water provides at that particular depth. So we know that if I am here below a height h of water plus the atmosphere, I have a total pressure from both. I know that the pressure of the atmosphere was 101,000, the pressure of the water unknown, but the total of these has to equal 513,000. If I find the difference, this tells me how much pressure the water had to provide. Now, I've then worked out the pressure difference between the top and the bottom of the liquid is 412,000. So I then use my pressure is rho GH equation. Okay, so pressure of the water is 412,000. If I rearrange this equation to find h, which is the depth, h is P over rho G. P is the pressure of the water, because I know that the height is the water height. So that's what I'm interested in, the water pressure. Okay, so the height is P over rho G, where it's 412,000 over the two values they give you in the question, gets you 40.816, which gives you 40.8 metres. In question 11, this is just one that you have to know off by heart. Which statement describes the relationship between mass and weight? Weight is the effect of a gravitational field on a mass. Okay, that's just something that you need to remember, please. The others are wrong. It's definitely not a magnetic field, so we can cross out B and D. Mass is the effect of a gravitational field. No, incorrect. Mass would exist regardless of whether or not it was placed inside of a magnetic field. Your mass in your body wouldn't disappear if we suddenly moved you to a place where there was no gravitational field. So you need to choose C. Okay. In question 12, a gas in a container is cooled, but the volume of the gas does not change. Which row describes the changes in the pressure of the gas and the kinetic energy of the gas particles? So, we know that temperature is a measure of the average kinetic energy of the particle, and we know that pressure is force divided by area. Now, we are told that the volume remains constant before and after, but the temperature drops, which means that the average kinetic energy of the particles drops. So we know we have to pick A or C because we know that the kinetic energy has decreased, because by definition, temperature measures the average kinetic energy. Now, if the particles have less kinetic energy, they are going to hit the walls less frequently. They're slower now, aren't they? So they're going to take more time to collide with the walls. So less collisions in the same amount of time means less force. Now, if the force drops over the same surface area because the volume hasn't changed, this means that the pressure also drops, giving us A. Excuse me. In 13, small pollen particles are suspended in water. This is Brownian motion. When viewed with a microscope, the pollen particles can be seen to be moving about irregularly. What causes this movement? Again, this is a memory question. You need to remember that we can physically see the smoke, or the pollen. Sorry, I've said smoke because it's often used with smoke. But pollen, so small pieces of pollen from a plant, can be put on top of water, and then we see them jiggle around, and we see them take this really erratic, random path. We just see the water underneath. We can't see the water particles because they're too small for our eyes to see. However, what's actually happening is the small water particles that are too small to be seen, but if we look at them under the microscope, they are also moving around, but it also means that the pollen then collides with them, and when it collides, there's a bounce, and it bounces off in a new direction. And so the pollen particles are being bombarded by the lighter particles of water there. In question 14, a bicycle braking system transfers energy from a kinetic energy store to an internal energy store. A motor converts energy from a chemical energy store, a battery, to a kinetic energy store. What enables these energy transfers? So, braking works, so as your wheels turn, you press your brake pads on the wheels, and friction causes the bike wheel to slow down. Okay, friction is a mechanical bit of work. So we know that the brakes works with mechanical. It then gives you a bit of a clue. A motor converts energy from a chemical energy store in a battery to a kinetic energy store. Anything that requires a battery is going to be part of an electrical circuit, and so it's electrical work done. It gives you D. In question 15, a wind turbine is 30% efficient. I'm going to turn that into a decimal value, 0.3. And has an output of 2.5 megawatts of electrical power. You have to remember that big M means mega, means times it by a million, times 10 to the 6. Okay, so the actual value in watts is 2.5 times 10 to the 6. What is the power input to the turbine? Efficiency is useful output compared to total input. I'm going to put it as a decimal value rather than having to deal with times 100 to convert between percentages and raw numbers. So 0.3 is the ratio of the useful output to the total input. We know the useful output because we're told it. So I just rearrange this equation. I multiply both sides by total input and I divide both sides by 0.3. And I get this big number here. Now, if I count here, I've got 1, 2, 3, 4, 5, 6. So I can write this as 8.3 times 10 to the 6. Okay? And that is 8.3 megawatts. So that gets me B. Okay, so in 16, a woman of mass 50 kilograms has 81 joules of kinetic energy. What is her speed? Okay, well, we start by writing the kinetic energy equation. KE is a half mv squared. I can replace some of the symbols with values that I know. 81 is a half times the mass, 50, times v squared. So I can rearrange and multiply both sides by 2 to get rid of the half. 81 times 2 is equal to 50v squared. I can divide both sides by 50. 81 times 2 divided by 50 equals v squared. Therefore, if I square root all of this, I must end up with v. And when I do that on my calculator, I get 1.8 meters per second. Now, question 17 was one of the more difficult questions on the paper, mostly because they give you a whole lot of information that you do not need. This is how they work out who their A-star students are. They throw lots of information at you and expect you to be able to work out which bits you need. Not all of it is helpful. A skier is pulled up a short straight rope at constant speed, so I'm busy annotating before I even get to the question. There's no acceleration, no resultant force, and no change in kinetic energy if we're moving at constant speed. Okay? The tension in the rope is 100 newtons. So the force in the rope is 100 newtons. And there is a combined frictional and air resistance force of 20 newtons, which will act in this direction, acting on the skier. The slope is 10 metres long, so that's a distance. So we've got 10 metres that we're travelling through. And there is a combined, and the skier rises 1.5 metres vertically. So we know that the skier actually also is gaining GPE. How much work is done by the rope pulling the skier up the slope? Now, work done is what we are being asked to find. Okay, so that is our main focus. So we write our equation. Work done is force multiplied by distance. Now, the work done is not the total work done. It's the specific work that the rope is able to do. So the force applied on the skier by the rope was only 100 newtons. So the force I'm interested in is just the 100. The distance that that force causes the skier to move through is 10 meters. So I'm literally doing 100 times 10. That's it. So I only actually needed this number and this number. They were checking that you could identify which ones you needed. So that then just gets you 1,000, gives you C. In 18, a car moves along a horizontal road. Its initial kinetic energy is 280 kilojoules. This is 280,000 joules. A constant resistive force of 200 newtons acts on the car. No other horizontal forces act. What is the kinetic energy of the car after it has travelled a distance of 300 meters? Okay, we know its initial kinetic energy. What we need to work out is how much energy it loses because of the resistance force. Okay, so the car is slowing down because a force is causing it to slow down. We know that the resistive force is 200 newtons, and that's applied for 300 meters. work done is force times distance. So the 200 Newton force multiplied by the 300 metre distance means that the car must have lost 60,000 joules of energy. So the final kinetic energy is its initial minus whatever it lost, gives me 220,000. In question 19, which statement about the particles of a substance after condensation is correct? Well, first things first, remember that condensation means a gas is turning into a liquid. So you are looking for a statement that correctly describes a liquid. That is just something that you need to remember. The particles are close to each other and they slide over each other, gives you A. Okay, we will end this video with a quick and easy one, memory. What is the lowest possible temperature, which is absolute zero, and what happens to the particles and the energy of the particles at this temperature? You have to just know that absolute zero is minus 273 degrees Celsius. A or B are the options. You also have to know that when the objects have minimum temperature, they have minimum vibrational energy, because remember, temperature is a measure of the average kinetic energy of the particles. So if we have zero temperature, so minimum temperature, minus 273 degrees Celsius, lowest temperature, I shouldn't say zero temperature, we know that we therefore have to have the lowest possible kinetic energy, gives us A. That's just one that you should really remember, please.